Okay, so here are the steps, what we're going to do. So first we'll express the u in radial form, this u plus expression we have, known as a function of r. So to do that, that is going to be 1 over kappa u star, where this is capital R minus r. This is again just that y plus I defined in last video. Not too bad. All we're doing is just that little expressing in radial form. That satisfies that. Next, remember what was critical for that friction factor is we needed to get this V bar expression, right? Because if we get this expression, what we're doing is we're modeling the pipe as just a constant velocity profile through it. So same rules apply for the turbulent flow. I'm still looking for this thing. So just the same methodology, right? We know that this, what I want, cross-sectional area. Not too bad though, right? This is 1 over area. Right? Same thing. The only difference is the function you're jamming in there. Okay? So extra credit. Go ahead and do that, right? Remember that remember that this u plus in last video, if you get the reference last video, but if you just want to watch this one, right, remember that the u plus is non-dimensional, so really it is a u divided by a u star, and then that u star is friction velocity, which is the square root of tau at the wall divided by rho. It's in the notes and in the last video, if you want to do it, go ahead. So you do these steps, what do you get? You get v prime over u star okay, not quite done. Chugging away. So for 3, we're going to rewrite this, right? Because v prime divided by this thing, same as this divided by rho tau wall. And you just make this squared and throw it in there. Okay. So this is just rewriting this part over there. So we'll have this equaling something. Step 4. Call the definition of a friction factor. Friction factors, we're defining them like this. Diameter of pipe, length of pipe. That is what the friction factor is defined as, laminar or turbulent. So you could be kind of stuck here, but there's one, right? And then the other thing is remember that laminar turbulent expression that we had before. This was going to be true regardless of laminar or turbulent flow. Okay? So one other way to express this friction factor is actually this. That's just subbing in expressions for another. If this is, let's say, the definition of a turbulent friction factor. Okay. So that's all fine and dandy, but then what you do is you take all these things, sub them together, and then you derive a friction factor for a smooth pipe. So what you end up deriving is an implicit relationship. Now what that means this is important, right? If you sub all of those last equations together and do an extra credit, actually do those processes is great. You end up having to get this relationship where this is now the turbulent friction factor, but it's on both sides of the equation. So you actually can't write out we can't solve for F in this equation. You can go ahead and try doing it, but the problem is you have this implicit relationship where this is this is in there, and you again get a Reynolds number. So right off the bat, we know that friction factors functions of the Reynolds number of the flow inside the pipe. These Darcy friction factors, whether they were laminar or turbulent, they're functions of Reynolds number. This is an implicit relationship, but it's still a function, right? Once you give me a Reynolds number, I can get the F. You just need to use a computer for this equation, actually. So up next, this is actually all for smooth pipes. So next step to really get the whole thing right, to really get everything right, is we want to talk about rough surfaces on the inside of pipes and get those friction factors as well.